Welcome to 2.2. Today we're going to talk about describing solution sets in R3. So we're going to start off with two formulas that are just generalizations of formulas you already know. The distance formula in R2 and the midpoint formula in R2 generalized to R3 by just adding that extra coordinate, in this case here and in this case here. Another generalization is the equation of a sphere with center ABC and radius r. That's the set of all points whose distance from ABC is r. Now that generalizes the fact that the standard equation of a circle with center AB and radius r is x minus a squared plus y minus b squared equals r squared. So let's do an example that uses some of these formulas. We want to find the standard of equation of a sphere with center C, and one point on the sphere is given as the point P. So we're already given the center. We're going to need the radius. And that's going to be the distance between the point C and the point P. And so in the distance formula, I'm going to let this be x1, y1, z1, and P will be my x2, y2, z2. And so the distance between C and P is going to be the square root of 0 minus 1 squared. So that's negative 1 squared plus positive 3 squared, and then plus negative 1 squared, and that's the square root of 11. So now we know our radius, and we know our ABC, which is the center, is 1, negative 2, 3, and we can just write down the standard equation of the sphere. X minus 1 quantity squared plus y plus 2 quantity squared plus z minus 3 quantity squared is the square root of 11 squared, which is 11. Okay, let's do one more of these. Complete the square to find the standard equation of the sphere. Okay, so we're going to have to complete the square on the x part, the y part, and the z part. So x squared plus 10x is x plus 5 quantity squared. Now when I FOIL that out, I get x squared, I'll put my scrap paper up here, x squared plus 10x plus 25. So I need to subtract 25 because x squared plus 10x doesn't have a 25 in it. So that's my correction factor, is subtracting 25. Let's do the same thing for the y's. Y squared plus 8y is y plus 4 quantity squared. But I've added on an extra 16 that wasn't there originally. So I'm going to subtract off 16. Again, that's a correction factor. And then finally with the z's, z plus 5 quantity squared, and again, subtract 25, correction, and then I have plus 41 equals 0. All right, now move the constants to the other side. So we have x plus 5 squared, y plus 4 squared, plus z plus 5 squared is, I'm going to have a positive 50, a positive 16, and a negative 41, and that's 25. So now my standard equation is x plus 5 squared plus y plus 4 quantity squared plus z plus 5 quantity squared equals 25. All right, and I wasn't asked, but I can see now that the center of the sphere is at negative 5, negative 4, negative 5, and the radius is 5. All right, so now let's talk about lines and planes in R3. There are three coordinate planes in R3. The xy plane, which is the plane you see there in green, and that's got equation z equals 0. X and y are free, but z has to be 0 when you're in the xy plane. The xz plane, which you can see there, is in purple because this is x this way, this is y this way, and z's going up. That's got equation y equals 0. That describes the xz plane. And finally, the yz plane, which is in teal, has equation x equals 0. And a good way to visualize things in 3D is by using this website, CalcPlot 3D. And I'll show you how to use that today. So let's describe some solution sets. And there's a set of rules here. For lines, I want to give 1 point on the line and the axis that the line is parallel to. And for planes, I want to give 1 point on the plane and the axis that the plane is perpendicular to. So this first equation, y equals 2. Well, there's 2 degrees of freedom here. Y is specified, but x and z are free. So I could imagine I'm going to get a plane, and indeed I am. I'm going to get a plane perpendicular to the y-axis through, I have to give 1 point that this plane passes through. Well, I know it passes through y equals 2. Now for the z and x coordinates, I can pick literally anything because x and z are free. So I usually just pick zeros. And there I go. The plane passes through that point and it's perpendicular to the y-axis. Now let's take a look at that on CalcPlot 3D. Here's CalcPlot 3D, and the default equation is a z equals over here on the left. To get a y equals, I need to go to select, and I want to select a function of the form y equals f of x. So I'm going to write down y equals 2. I'm going to graph that, and I'm going to unclick the default graph, and there I've got my plane y equals 2. And I cleaned it up a little, and you can see it is indeed perpendicular to the y-axis, and it passes through 0, 2, 0. Okay, next one. X equals 2, y equals negative 3. Well, now both x and y are specified, so there's 1 degree of freedom. Z is free. So in this case, we're going to get a line, and we're going to get a line parallel to the z-axis, because z is free, and a point that it passes through. Well, we know x has got to be 2 always. Y's got to be negative 3 always. Z can be literally anything. I'll just choose 0. So let's visualize that on Calc 3D. I want y equal negative 3, and I'm going to need an x equal, so I select x equals 2, and you can see here that what's happening is I'm getting the intersection of 2 planes. The blue plane is x equal 2, the purple plane is y equal negative 3, and they intersect in this line here, and that is the line that's being described, and you can see that it is parallel to the z-axis, okay? Back here on part 3, x, y, and z are being specified, so there are 0 degrees of freedom left. This is simply a point. This is a point, and it's the point 2, negative 3, 5. And what's happening there is I'm taking the 2 planes, x equal 2, y equal negative 3, and I'm intersecting with a third plane, z equal 5. And there's the plane z equal 5 there, and you can see the 3 planes intersect in a single point. Okay, now let's do some other problems going the other direction. Here, we're given the description of the solution set, and we want to describe it with a single equation or a pair of equations. So we've got a plane parallel to the yz plane through the point 3, 2, negative 1. So if we're parallel to the yz plane, that means we're going to be perpendicular to the x-axis. Okay? Now a plane passing through 3, 2, negative 1, perpendicular to the x-axis is simply going to be x equals 3. So let me go back to Calc 3D and show you that when I specify x is a certain number, I'm getting a plane which is perpendicular to the x-axis and parallel to the yz plane. Okay, a plane perpendicular to the y-axis. So now same thing, except I'm going to specify y. Y equals 2. And if you wanted a plane perpendicular to the z-axis through that same point, you would go z equal negative 1. All right, the next one, a line through this point and parallel to the x-axis. So that we only want 1 degree of freedom here, and since we're parallel to the x-axis, x is going to be free. We need to specify y and z. So y equals 3. We're going to take that plane and intersect it, so comma, with the plane z equal negative 1. Those 2 planes intersect in a line which is parallel to the x-axis. And you can convince yourself, go to CalcPlot 3D yourself and plot those 2 planes just for practice. You'll use that program a lot in this class. Finally, the plane through 3 points. Now, typically, this is going to be a difficult problem to solve, and we'll spend some time on this later in the course. However, in this case, it's not a difficult problem to solve, because if we look at these 3 points, we see that the y-coordinate is identical on each one. So this is simply the plane y equals negative 8. Okay, and that is the end of this section.